Sequential continuity. Now let us discuss the definition of sequential continuity. The continuity of a function at a point C is checked by examining the nearness of values x about C and corresponding nearness of values f of x about f of C. So we can consider the sequential version of continuity at a point. This helps us to explain the continuity without using the epsilon delta concept. Theorem. A real valued function defined on a subset A, subset of R, is continuous at C element of capital A if and only if for every sequence xn in A that converges to C, the sequence f of xn converges to f of C. Let us see the proof. Let f be continuous at C. Then for each epsilon greater than 0, there exists delta greater than 0 such that absolute value of x minus C less than delta implies that absolute value of f of x minus f of C less than epsilon. We can refer this as step 1. Suppose sequence xn is a sequence in A with limit xn equal to C. Then for delta greater than 0, there exists a positive integer k such that absolute value of xn minus C less than delta for all n greater than or equal to k. We can refer this as step 2. From 1 and 2, by taking x equal to xn in 1, we get absolute value of f of x minus f of C less than epsilon for all n greater than or equal to k. Therefore, limit f of xn equal to f of C. Hence, the sequence f of xn converges to f of C. Conversely, suppose that for every sequence xn in A that converges to C, the sequence f of xn converges to f of C. Assume that f is not continuous at the point C. Then there exists at least one x element of A and one epsilon greater than 0 such that for all delta greater than 0, 0 less than absolute value of x minus C less than delta implies that absolute value of f of x minus f of C greater than or equal to epsilon. Take delta equal to 1 by n. Then for each positive integer n, we get xn element of A such that 0 less than absolute value of xn minus C less than 1 by n implies that absolute value of f of xn minus f of C greater than or equal to epsilon. We refer this as step 3. From 3, it follows that sequence xn converges to C, but sequence f of xn does not converge to f of C. This is a contradiction. So f must be continuous at C. In the following example, we check the continuity of function f of x equal to 5x minus 3 at the point x equal to 1 in the closed interval 0 to 2. Here f of 1 equal to 2. Suppose sequence xn is any sequence in closed interval 0 to 2 that converges to 1. For example, we take sequence 1 plus 1 by n, and this is a sequence in closed interval 0 to 2 that converges to 1. By the property of sequences, sequence 5xn minus 3 converges to 5 minus 3 equal to 2. So the sequence f of xn converges to f of 1. Hence, f is continuous at x equal to 1. Let us check the continuity of the function f of x equal to x square if x not equal to 2 and f of x equal to 1 if x equal to 2 at x equal to 2. Here f of 2 equal to 1, consider the sequence xn equal to 2 plus 1 by n. This sequence converges to 2. Then f of xn equal to xn square equal to 2 plus 1 by n whole square, which is equal to 4 plus 4 by n plus 1 by n square. This shows that f of xn converges to 4. Therefore, limit f of xn equal to 4 and not equal to f of 2. Hence, f is not continuous at x equal to 2. Another example. Let f be a function defined on R by f of x equal to 1 if x is rational and f of x equal to minus 1 if x is irrational. Let us check the continuity of the function f on R. Let a be a rational number. Consider the sequence xn equal to sequence a plus root 2 by n. This is a sequence of irrational numbers and limit xn equal to a. F of xn equal to minus 1 for all n. So the sequence f of xn converges to minus 1, but f of a equal to 1. Thus, the function is not continuous at any rational number. Let b be an irrational number. Consider the sequence yn of rational numbers that converges to b. This is possible by density theorem and squeeze theorem for sequences. Then sequence f of yn converges to 1 and f of b equal to minus 1. Thus, the function is not continuous at any irrational number. Hence, f is not continuous on R. We can make the following remark. We cannot explain the continuity of the above function with the help of a graph. In the next example, we examine the continuity of the function defined by f of x equal to sine 1 by x, x not equal to 0, and f of x equal to 0 at x equal to 0. We check the continuity at the point x equal to 0. Let's see xn equal to 1 by n pi, where n equal to 1, 2, 3. Then limit xn equal to 0. F of xn equal to sine n pi equal to 0 equal to f of 0. So, limit f of xn equal to f of 0. This must be true for all sequence xn that converges to 0. Consider the sequence yn, where yn equal to 1 by 2n pi plus pi by 2. Then limit yn equal to 0. F of yn equal to sine 2n pi plus pi by 2, which is equal to 1, not equal to f of 0. So, the function f is not continuous at x equal to 0. In the next example, we check the continuity of the function defined by f of x equal to x sine 1 by x when x not equal to 0, f of x equal to 0 when x equal to 0. Here we check the continuity at the point x equal to 0. Suppose sequence xn is a sequence of real numbers such that limit xn equal to 0. Then by the definition of convergence, for any given epsilon greater than 0, there is a positive number k such that absolute value of xn equal to absolute value of xn minus 0 less than epsilon for all n greater than or equal to k. We refer this as step number 1. Then absolute value of f of xn minus 0, which is equal to absolute value of f of xn equal to absolute xn sine 1 by xn less than or equal to absolute value of xn, since absolute sine 1 by x less than or equal to 1. So, from step 1, it follows that absolute value of f of xn minus 0 is less than epsilon for all n greater than or equal to k. Thus, sequence f of xn converges to f of 0. Hence, f is continuous at x equal to 0.